On my last page of notes, I'm going to actually work through some examples where we get a single point. So again, I see that I have 3 equations, 3 unknowns, and I need to choose a variable to eliminate. On the previous 2 examples, it didn't matter what I eliminated. But on this particular example, what I notice is that equation A, the y variable is positive, but equation B and C, the y variable is negative. If I choose to eliminate y in this case, it's going to be a little easier for me because I do not have to worry about distributing a negative. So the first thing that I'm going to do is decide to eliminate y, and I'm first going to compare these first 2 equations. To eliminate y, I do not need to do anything to equation A, but equation B, the entire thing needs to be multiplied by 2. So as you can see here, I've kept equation A completely the same, and I've taken 2 times my entire equation B. When I add them together, I get my new equation that I'm going to call D. Sometimes students are concerned when they get a 0 on this right-hand side, and this 0 is okay as long as you still have variables on the left-hand side. The important thing to understand is when we go back to eliminate y, it's crucial that we use all 3 equations. So in my first step, I used equations A and B, so my second step has to use equation C. So for equation C, I'm going to again use equation A that I'm going to multiply by 3, and equation C I'm going to multiply by 2. There are many ways to do these problems as long as you eliminate the same variable both times and use all 3 equations, you'll be fine. I distributed my 3 to equation A, I distributed my 2 to equation C, and I add, and I'm going to call that equation E. At this point, if you are doing it correct, then you should have 2 equations that both have the same unknowns. Those 2 equations can then come together to create a new system of equations. Now this particular system is very simple because I can see that my variable z already has the same coefficients but opposite signs. So I don't have to do anything extra here. I can just add them together. If I add them together, I can easily solve for my x. At this point, I basically need to rewind everything that I've done, so I continue just working backwards. Now that I have x, I can substitute that back into one of my equations that only has 2 unknowns. So if I substitute x into my equation D, I could have done E, but I chose D. If I substitute x into D, I can now easily solve for z. Now that I have x and z, I can substitute those variables back into one of the 3 original equations. I chose equation A. I simply substitute and solve, and you'll notice that our answer is very clean numbers. Typically, when we're working with a system of 3 variables, as long as it's not a word problem, these answers usually turn out much nicer than our systems of 2. The last one that I'm going to look at is a word problem. Systems of 3 variables are very commonly applied for our word problems. So when we're looking at a word problem, we're looking for what I often call the totals. So in this case, that there are 49,000 seats in the stadium. If I glance to the end, because I've already read the problem, I see that total, they even use the word, total revenue is 1,419,500. And then if you read this carefully, you'll find that there's another total or relationship in the problem where it says the number of seats in the middle and bottom together, that gives you your total or relationship, equals the number of seats in the upper. So when I look down below, you can see that I've already written these 3 equations for you and how they relate. So my 49,000 was my total number of seats, upper, middle, and bottom. my total revenue of $1,419,500, I obtain that revenue based on how much I charge for each of my types of seats. So from the problem up above, I can see that it's $25 for an upper seat, $30 for a middle seat, and $35 for each of the bottom seats. My last equation is the last relationship that I saw, and that's the middle and the bottom together equal the upper. Now, this problem is a little bit different because what I can see is this last equation has actually already been solved for the variable u for me. So this problem is actually more easily going to be done initially with substitution. So the first substitution that I'm going to do is going to be combining equation C with equation A. So I can take u that I know is m plus b and simply substitute it. Now, I'm going to combine my like terms and see now that everything here is divisible by 2. So I get my new equation D after dividing through by 2. Remember, all three equations have to be utilized. So I combined equations C and A, and the next that's going to be easiest is to combine C and B. So when I combine my equations C and B, my m plus b substitutes in for my u. Remember parentheses. Now all I'm going to do is distribute my 25, collect my like terms, and because these numbers are rather large, I'm going to divide everything here by 5 just to make them a little bit smaller. So now I have two equations, two unknowns. That's my new equations D and E. So I bring those together, and when I bring those together, what I can see is that the easiest way for me to solve that system is going to be to do some elimination. I'm going to take my equation D, and I'm going to choose to eliminate m. Remember, it doesn't matter which variable that you choose. So equation D times a negative 11, distribute my negative 11, add my two equations together, and now I have solved for my first variable. Again, just unwind, take your b, and substitute it back into either one of our equations. Of course, equation D is the easiest to work with, so when I do that substitution, I get my answer for m. Now that I have two unknowns, I can go back and substitute into any one of the three original equations. Of course, I'm solving for u, so equation C is going to be the easiest. And there's my final answer.